Welcome again to the Applied Business Statistics course and on topic 6, the second part, which is on analysis of contingency tables or the chi-square test or analysis of goodness of fit test. And in the last session, we concentrated on the analysis of goodness of fit test and stated that the analysis of contingency table is a special case of the analysis of goodness of fit tests. So in this session, we are going to concentrate on analysis of contingency table among the chi-square tests. So what is contingency table? It is situations involving multiple population proportion or frequencies. Two or dual population frequencies or population variables or phenomena. So we use to classify sample observations according to two or more characteristics. We concentrate usually on two characteristics. Also called the cross-tabulation tables. As we mentioned in the previous section, we have cross-tabulated data of two variables. These variables are categorical. Both of them are categorical. So we have two categorical variables in this analysis or this situation. So an example of the contingency table is left-handed against gender. So we have two phenomena or two variables, the hand preferences and gender. Whether there is a relation between these two variables or no relation between them. So we have dominant hand left against right and gender males against females. So we have two feminine the dominant hand, whether it is left or right, and the second variable, male and females. So we have two categorical variables. Categorical variables is not doesn't take numbers, it's not numeric variables. So we need to test whether there is a relationship between these two variables. So the null hypothesis is hand preference is independent of gender. That's always the null hypothesis for analysis of contingency tables. Always the null hypothesis of the contingency table test or chi-square test is that the two variables are independent. With two variables here and the preference and gender. So its note is hand preference is independent of gender. The alternative hypothesis is that hand preference is not independent of gender. So we have these two hypotheses and we want to test these hypotheses based on the data. The data, as we mentioned, is a cross-tabulation of sample data. So the sample results organized in contingency table of cross-tabulated data. So it is like that. We have the table here, gender is male and female first and female, and hand preference is left and right. So that means we have 12 females left-handed and 108 females right-handed, and we have 24 males left-handed and 156 males right-handed. So we need to test whether there is a relation between hand preference and gender. So the summation of the rows like that. This first row is 120 and the second row is 180. And there the column sums are 36, the sum of two values here, and the column sums like 246. The overall sum, which is over the sum of all sums of columns, or the same here, the sums of all sums of rows is 300. So 220 females, 12 were left-handed, and n equals 300. Okay, now the logic of the test is as follows. So we have two hypotheses: the null hypothesis and the preference is independent of gender. The alternative hypothesis, as we mentioned, hand preference is not independent of gender. If H naught is true, then the proportion of left-handed females should be the same as the proportion of left-handed males. Then the two proportion above would be the same as the proportion of left-handed people overall. Right? So that's the philosophy of the test, but we do not need to always follow these steps of calculation of the expected values. We want to calculate the expected values under the null hypothesis, but just to understand the basics or the philosophy of the test, we explain it like that. So we have the overall probability of left-handed will be 3/6 of all the left-handed divided by 300, which is 12%. 12%. So probability of left-handed and female is equals probability left hand and males, and it will be 12%. So we would expect 12% of the 120 females and 12% of the 180 males to be left-handed. That's the expected value should be the same, 12% and 12%. So if, we would expect from 12% of 120, that means 14.4 females, which is approximately 14 females to be left-handed. That's expected value under the null hypothesis. The expected number of females to be left-handed under the null hypothesis is expected to be 14. And the expected number of males to be left-handed is 21.6, which is 22. 22 males to be is expected to be left-handed. That's the expected values for males and females to be left-handed. So we the same we can get the right-handed ones. As I mentioned that we do not need to understand everything in philosophy, but we have a rule here, a formula to calculate the expected value, which is very easy formula to calculate the expected value. So for every cell in the table, in our example, we have a 2 by 2 table. Could be 2 by 3 or 3 by 4 or some whatever. It doesn't matter. So we have 2 by 2. So every cell in the table, we calculate the expected value like that. We go to its row total and its column total, multiply them by each other and divide the result by the total sample size. Again, each cell, we take the total of the rows of that cell and multiply it by the total of the columns for that cell and divide the result by the total sample size. We get the expected value for that cell. We repeat that for all cells in the table, but not the totals. For all cells of the tables, inside the tables, but not the totals. So E11 equals 120, which is the first total, row total, and multiplied by 36, which is the first column total, divided by the number or the total sample size, which is 30. We get 14.4. 14.4, and we go on. So we at the end we get these results. observed against expected frequencies. Observed against expected frequencies. So we can put it in each cell. So we have the observed and we calculate the expected using that formula and put it different color or in the corner sometimes. Observed and expected. For each cell, we calculated in the same way. So we get the first cell, expected value is 14.4, and for the second cell, 105.6, and so on. The total remains the same. We are not changing, so we do not need them here. But we need observed and expected values for each cell and use the formula actually, this formula which we mentioned earlier, the same formula. The sum of all rows and columns, all in the table, that means sum of rows and sum of columns, that means the sum of all cells in the tables. For each cell, we have observed value minus expected value squared divided by expected value for each cell. And that's the chi-square test. And that, in that case, in cross tabulation, rows and columns, the degrees of freedom will be number of rows minus 1 times number of columns minus 1. And that's the test statistics. So OIJ is the observed frequency in the cell IJ, ith column, ith row, jth column. EIJ expects the frequency in the cell IJ, ith row and jth column. So R is the number of rows and C is the number of columns, and that's the formula. That's the rule, right? So in our example, we have these values we calculated earlier, the expected values, and we have the observed. So we apply this rule. Chi-square equals 12 minus 14 times 4 squared over 14.4 plus 108 minus 105.6 squared over 105.6, and so on up to end. We get the sum equals 0.6848. That's the value of the computed test statistic. Computed test statistic. So we have the critical value of the chi-square from the table with 1 degree of freedom. Why 1 degree of freedom? Because the number of rows is 2 and the number of columns 2. So 2 minus 1 times 2 minus 1 will be 1 times 1 equals 1. So that's the computed one, the computed statistical value, statistical test, computed statistic, computed test statistic. But using this data, we get the critical value from the table with 5%, 5% or 0.05 significance level, and with 1 degree of freedom, we get 3.481, and it will be this here. That's the critical value. And we reject the null hypothesis if the test statistic, computed test statistic, falls in this area. And we cannot reject the null hypothesis if it falls in this area. And in our case, it falls in this area. That means we cannot reject the null hypothesis. And we can conclude that gender and hand preference are independent. They are independent. So we do not reject each note and conclude that gender and hand preference are independent. So we cannot say that there is a relationship between gender and hand preferences, right? Finally, chapter summary, we use the chi-square goodness of fit test to determine whether data fits specified distribution or not. So as example, we have example of the discrete distribution uniform, and we can have, but we omitted example of continuous distribution. So we then use contingency table to perform a square test of independence. We compared observed cell frequencies to expected cell frequency, and that's all what we need to talk about in this chapter. That's all or this unit, and we finished that unit. Thank you very much, and see you in next unit. Bye bye.